In the name of Allah, starting maybe our last class. So today could be our last class, and if we have other classes, it would be for your discussion, your question and answer for the final exam and whatever you want regarding the course. If it's okay with you, at the end of this class, we could take a group picture together also here. So yeah. So everybody, please be there until the end of the class. Maybe we could finish it faster. Okay, any questions? Last time we have talked about multiplication and division. Yeah? So any questions? Okay, let's look at the reflection to see what did you write there. We had two questions. Okay, it was unsigned overflow, which is not related to multiplication and division, but it's something that you could think about it regarding the addition and also the division. Okay, the first question, I even might not know the answer, so let's see how did you write it, and we have to think about it. Think of something, some way to find the overflow. In MIPS, unsigned add doesn't care about the overflow. Signed addition and signed subtraction in MIPS, if there is overflow, then what happens?
Exception.
Exception. Perfect. Exception. That's what MIPS does. It goes to exception. It stops the program, goes to exception handler, which is a specific address in the code memory. Then it does something, and at the end it can return to whatever place that generated that exception. But for unsigned, it doesn't do anything. It doesn't do anything. So let's say that you are writing a program and the overflow is important for you. You would like to know if there is overflow for addition. How do you do that? Okay, let's see, what did you write? So starting from the first algo. Algo is here? No algo? Seems good, but since he's not here, or she is not here, I don't read it. Dangshi? No? Absent? Kevin? Yeah, Kevin. No? Kevin was there every time. This time he's not here. Omar? No? Maybe you are here, but you don't show up. You don't raise your hand. Okay, Harling, good, yeah. Harling, let's see, what did you write, Harling? In unsigned addition, a good indicator would be the carry. Okay, how did you find if there is a carry or not? There is a set of MIPS instruction that could also detect, but there is no carry also in the MIPS. So again, the question remains as it is.
Yeah, that's why I said.
Yeah, so that's the, so yes, overflow in unsigned addition means carry. If there is a carry, then it means that there is overflow. But so how do we detect it? So Harlan is suggesting that could also be answered using some mathematics. Okay. We are adding unsigned T1 and T2 and putting the result in T0. Then you are doing NOR T1 with 0. So you are converting it. Okay. So let's see, what do you do? So T3 is now the invert of T1. Okay. Then you compare set less than unsigned T3 with T2. Okay. So then what happens? Oh, okay, you are writing that. Why didn't I see that? Okay, line 1, unsigned addition is performed. Okay. Line 2, T3 now stores the funds complement of 1. Okay. Line 3, this checks if 2 to the 32 minus T1 minus 1 is less than T2. If this is rearranged, then it is equivalent to checking if 2 to the 32 minus 1 is less than T2 plus T1, which can also be indicative of overflow incident. Let me do an example until I understand, because it might be complex. Finally, you could have a branch instruction. Okay, so let's do an example. Let's assume that I am adding two numbers, for example, a 32-bit number, or even a small one, maybe 4-bit number. 4-bit number. So let's say we have number 0110 plus 0100. It should generate, or, oh, it's unsigned, sorry, it's unsigned. So let me put 1 here and also 1 here. So we have 1110, which is 14 in decimal. And we have 1100, which is 12 in decimal. So the total would be 010111 with a carry of 1. So the total would be this, which has overflow, of course. So let's see the Harlan's suggestion. Knowing T1. Okay, so we actually calculate 1's complement of this, which would be 0011. So this is T1 bar, and this is T2. So this is T2. Then we compare T3 to T2 with unsigned, SLTU, set less than unsigned. So T3 to T2, T3 is this one, T1 bar, T3. We compare this to T2, unsigned, which is less, okay? So you are saying that if this is less, T0, you don't look at T0 at all.
Yeah, because it's the 1's complement is basically saying 2 to the 32 minus T1 minus 1. And so, like, it should make sense that...
It's interesting. Let's see. Then you are comparing T3 to T2, which is less than. So in this example, we get 1 for T4, okay? T4 becomes 1. Now, checks for this, finally, you could have a, so if it is 1, then it means that there was overflow. Okay, let me put another example. So you are comparing this to that, which is less than that. I guess you are right. Let me put something that when we calculate 1's complement, it is not less than that. The original value was 1110, so if I make it 1101, when I do 1's complement, that's good. So instead of that, I am writing 1101. 1101. Oh yeah, I guess you are right. If I add this together, what would be the result? So 00110. 1110 is 14. 0010 is 2. And the result has overflow, but your method doesn't work here. You are right, but maybe you are missing one. Let me show you. Okay, this is T0. Okay, for your example, this is T0, and this is this is T1. This is T1. This is T2. So then you calculate T3. T3 would be 1's complement of that, which is 1101, okay? 1's complement of that, 1101. So is 1101. You compare T0 to T2. If it is less than, then you accept that. Oh, okay. If it is not less than, let's say that it is the same of that, 1110. If it is 110, you are right. I got your point. Did you understand what Harleen suggested? She's suggesting that when we add two numbers, unsigned numbers, the maximum number that we can get out of this is 1111 without overflow. If there is more than that, then we have overflow. So to find out that, she's actually doing 111 minus this, and then compare it with that one. Very good. Perfect. I now understood the method. So 1111. For 32-bit, it would be 111111 32 ones, which is 2 to the 32 minus 1. So that's exactly what she did here. So 2 to the 32 here, you see, 2 to the 32 minus T1 minus 1. So it compares that with T2 here. If it is less than that, then when we add them together, it fits. If not, it will make overflow for sure. Very good, very good. Yes? Another example? Yeah? You tell me. Give me two 4-bit numbers, okay? To see how it works. When I did the example, I understood what does she mean and what is the concept. The concept is actually 1111. The thing is this. If they added up to this or less than that, then that's okay. If it is more than that, then it means that we have overflow. So you tell me two numbers. 1, yeah? 2, 0, 0, 0, and you mean? 1, 1, 0, 0, okay? Or something else, I didn't hear you. 1, 1, 0, 0. The other one? 1, 0, 1, 0, yeah? So it has overflow because 1, 1, 0, 0 is 12, 1, 0, 1, 0 is 10. When you add them together, you get 22, which is more than 15. So it has overflow for sure. So what was the algorithm? So we are doing ones complement of that. The ones complement of this one would be 0, 1, 0, 1. If this is less than that, then we will have overflow. If it is not less than that, then we don't have overflow. So here you see this is less than this. So if you add them together, they have overflow. Very good. Okay. There might be some other solutions that you had also. I don't know. We can see some of them. Okay, the laser, yeah? Laser, yeah. So that's the question. How to see whether there is carry out or not. Because in MIPS, we don't have anything to detect carry again here. If you have other processors, they do have flags like carry, overflow, negative, these things they have. But in MIPS, we don't have any flags. Just in sign addition or subtraction, we do make exceptions. That's just that. We don't have any flag. And you see, the whole idea of designing MIPS is to make it simple, because making flags means more hardware. You have to make your ALU somehow to generate flags of Z, flags of V, overflow, flag of N, negative. So we didn't do anything about that, just the Z because of the branch unequal instruction that we had. Only Z, and that's it. And somehow we just compared them in SLT. Very simple. We made it as simple as possible. So we don't have carry flag, we don't have overflow flag in MIPS. We have to, if we need that, we have to do it ourselves as, for example, as Harleen suggested. Name, what did it? Name is suggesting something else. Name is not here. Oh yeah. So I don't go through it, but it seems that it is another way, not inverting. You are XORing together. I have to read it, but it is another way. I will see it later. Very good. So the next question was division. So that's some kind of practice. It didn't have any kind of complexity that you need to think. It's a practice. So Dangshi is here. She's not arrived. Okay. Harleen, yeah, no. Kevin, no, not arrived. Lazar is here. So let's look at Lazar. So 1011, 0011. So 1011 is 11. 0011 is 3. The result should be, I do it myself to make sure that what I've done here is correct. So you could do it also in your exam. You calculate the decimal and then try it in decimal, find the answer, and then compare it with whatever you get. Because we are more familiar with decimal numbers. Anyhow, 11 divided by 3 is 3. Quotient is 3, and remainder is 2. 3 times 3 is 9, and the remainder is 2. So let's see what Lazar has done. Let me see. But Lazar is saying that the remainder is 1. So it's...
I just realized my mistake. This is when I came to class.
So what was the problem? The sign problem or something else?
No, I have brain.
Okay, so we could see where did you make the mistake, okay? Okay, it's okay? Okay, so let's see, it's a little challenging. 0011, quotient would be also would be, and honestly done, you get with 1 remainder. So we know this because 1011 minus 0110. What is 0110? Oh, okay, it's shifted, right? You have shifted that, so it's 0. So it should be 0. Okay? Yeah, you found the problem, or not? Yeah? No? Yeah, so, yeah, no? Maybe 1, no. So it's hard that I have to go through it to find your problem. But it seems that you haven't done it right. 1011, you should subtract it from 0011. I don't know why you have done this. No, 0011. Here, you have to start from here. So that's the problem, I think. Tony is here. Okay, Tony. So you are not online this time. Good. Here. Okay. 0011, what did you get? At the end, the quotient is 3, the remainder is 2. So you are right. Let's see what have you done. So quotient 0000, divisor is 0011, shifted 4 times to the left, and remainder starting with the dividend, which is 1011. So the first one, you decrement this, subtract this from this, which would be negative, so you make it back. So 0, you insert 0 to the quotient. Again, shifting the divisor to the right. Now we have 1100, still this is more than that. So if you subtract, you get negative number. So again, making it back. So again, we have 1011 at the remainder. Now we have 1100. Still, if we subtract them, we get 1100, 110. but still it is more than that. It is more than that. How did you find a positive number? No, Tony? 0.0001100. This is the divisor. The remainder is this. When you subtract this from this,
I copied wrong.
yeah, but
I did it on the paper,
but your answer is right. So here, yeah, okay. I guess this step. When you subtract this from this, you get the negative number, and since it is negative, you keep it, and you start inserting 0 to the quotient. But here, that should be the 1. Let me see, how did you write here? So 110, and the remainder is 1011. When you subtract this, 1011 minus 110, we get this. 101, and it is positive. Since it is positive, it is acceptable, and then we insert 1 to the quotient. 1 to the quotient and keep it, not restoring it to what it was. So this is correct. So this number, you are right, you are doing something wrong in number 3, but here it's correct, number 4. Then what we have now, the remainder is 101. And if we write it, the divisor, it is 11. The remainder is 101. When you subtract them, you get 2. And it is positive. Since it is positive, we insert another 1 to the quotient. So the quotient will be now 1, and the remainder will be 10, and that's it. That's the last step. So the remainder is 10, means 2, and the quotient is 11, means which is 3. Okay, Tony? So something you haven't done right at this position. The result is negative, and then so this is for sure one of your questions in the exam. You have to do the division. So to go through the steps and find out the division. Okay. Any questions? Now let's continue for the last part of the course, which we will talk about floating point. Up to here, whatever we talked was integers. The integer representation of the numbers. For example, when we are talking 12 in decimal, the integer, it is an integer. It doesn't have any kind of fractal part, so fraction part. So it is 1100. We represented it 110. Now we are talking about the floating point, the numbers with fraction, okay, like 1.5. like 23.34, which is it has a fraction part. In decimal, how do we do that? In decimal, we have some kind of normalized representation. You know that in a school. You learned it in a school. So what we do is this. For example, this is the normalized way of representing a floating point number. The mantissa, this part should be something between 1 to 10 times an exponent of 10. This is how we represent the numbers. Remember? You had it in school, yeah? Yeah? Anybody, everybody, yeah? We had it. For example, if you show it like this, it is not standard weight. It is not normalized. It is a representation, but it is not normalized. For example, here we have seen, we are writing 002, 2 over 1,000, 2,000, which is not normalized, but this is another floating point number. So this is a floating point number. in the normalized way, it should be the mantis part, the mantissa part would be between greater or equal than 1 and less than 10. It should be like that. The same thing in binary. So in binary, again, the parts which is multiplied by an exponent of 2 should be something between 1 to 2. Here we have 1 to 2. So that part should be something greater or equal than 1 and less than 2. 2 means 1, 0. Less than 2, okay? So it is something like that. 1 point something times 2 to the something. This is exponent, this is mantissa, okay? Yeah? The same thing. But we are not familiar with this one, but we have to make practice of that. And also, remember that we have a sign. Sign is something separate. So it could be a positive number or negative number. Either way, you just have the sign separately. But the value is something between 1 to 2. Okay? I will give you examples to show so you know what I am talking about. There are two types in usually programming languages like C, Python, and also in MIPS also there are two implementation of floating points. One is, in C we call it float and double the type of the number. Float means actually we call it single precision, which we will see later, which has 4 bytes, 32 bits representing that, and double is 64 bits, 8 bytes for representing that number. So double precision means bigger binary number, which of course should have more resolution and more magnitude. It can support more magnitude. So we have a standard by IEEE called 7454, and the standard was developed because there were different kind of representation of floating points in different architectures, in different programming languages. So we wanted to make them united, just everything would be the same. So the IEEE presented this standard. So now the code is portable. If you have something in a machine, you can do the floating point representation is the same in another machine. If you have something in C, written in C with a floating point, then it is the same in, for example, Fortran or Python. Everybody now use this standard. There are two representations, one with 4-byte representation, the other with 8-byte. So it is either single precision, 32-bit number, or double precision, 64-bit number. How do we represent? Okay, this is the one. Look at that. It is, for example, the whole number, which is either 32-bit or 64-bit. The first bit is the sign bit. It is either 0 or 1. So if it is 0, means that this number is positive. If it is 1, then now this number is negative. Then we have the exponent part, which would be 2 to that exponent, and which we have the fraction part, the mantissa part, which will be something between 1 and 2. Okay. Since it is always between 1 and 2, then we don't need to put 1 there. We know that there is a 1 there. So we just get the fraction part. Here would be 1 plus fraction. And for the exponent, since we are going to have positive exponents and also negative exponents, we use this and we will put a bias for that, and that would be the real exponent that we put 2 to that power. I will give you an example later so you understand what I mean. So the number, the exponent that here is 8 bits for single precision. So 8 bits means a number between 0 to 255. So that would be the exponent. And that number is going to be decremented by the bias, which I will give you the bias. And then that's 2 to that number would be the exponent part. And the fraction part is 23 bits, 23 fraction bits. For example, this is a fraction. I will put 0 for the whole 23, except these 2, 1, 1. So this fraction is how much? We have 1 here, so it means 1 times 2 to the minus 1. We have another one, which is times to the 2 to the minus 2, and the rest is 0. So 1 times 2 to the minus 1, if I want to make it decimal, 2 to the minus 1 is 1 over 2, which means 0.5. So this is 0.5 plus 1 times 2 to the minus 2. 2 to the minus 2 means 1 over 2 to the 2, which is 1 over 4, which is 25.25. So this number is 75. This is the fraction part, and this is the exponent. If it is double precision, then our exponent would be 11 bits. 11 bits means 2 to the 11, which is 2048. So this is a number from 0 to 2047, and then the bias will be decremented. So that would be some number, positive, negative. I will show you what it be. And the fraction part in double precision is 52 bits. Very good resolution. 52 bits of resolution for the fraction part. Let's see some examples. Okay. So as I told you, the significant, I mean the fraction part should be something between 1 and 2, either greater or equal than 1, less than 2. And since it has always more than 1, less than 2, then there is a 1 here. So there is a 1 with the fraction. So we don't put 1 here in our code to have some kind of bits reserved, bits that we don't want to put it there. We know that there is a 1 there. Significant is fraction with the 1 point at the beginning of that. Exponent is actual exponent plus a bias. What is the bias? Let's see. Okay. In single precision, the bias is 127. In double precision, the bias is 1203. Let's do an example. Okay. So, oh no, this is not an example. It's still about the floating point. 2 exponents, 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 1 is reserved. You cannot use them for regular numbers. They have a specific meaning, which I will tell you later, not here. Whatever I told you, let's find the smallest value that I could represent by the floating point, the single floating point. So the single precision floating point is 32 bits number. We had a sign, so it is either positive or negative. And then we have 8-bit exponent. So the smallest number has an exponent of 1, because 0, you cannot use 0 and you cannot not 1, 1, 1. So the smallest one would be 1. So 0, 0, 0, 0, 0, 2, 3, 4, 5, 6, 7, 8. This is the smallest exponent that we can have. And then the fraction part what would be the smallest fraction part? 0, if you put everything 0. So the exponent would be 1, and the fraction would be 0. So what would be the number? Let's see what is the number. Let me write the whole number and then calculate what it is. So the whole number is, if it is positive, 0, then 8 bits with 1, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. So this is the exponent part. The fraction part, which is how many bits? 23 bits. How many bits? The fraction is 23 bits. So the fraction part is 23 bits. I want to make it smallest one, so I put 0. 23 bits of 0. This is the number. 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. What is this number? This number is plus, it is positive. The exponent is 1 minus bias. Bias is 127. So 1 minus 127 is minus 126. So it is 2 to the minus 126. And the fraction part is 0. So 1.0, which is 1. So the number would be 1 times 2 to the minus 126. What is that? What's this number? It's a very small number. So this is the smallest number that we can represent in single precision floating point. I guess I have it here. So it is around 10 to the minus 38. 10 to the minus 38. It means that there are 38 zeros, and then I am writing in decimal. 0, 0, 0, 0, 0, 0, 38 decimal numbers. So the precision is that, which is not bad. 38, 10 to the minus 38. Largest value. For the largest value, we cannot use this for the exponent. So the largest one would be 1, 1, 1, 1, 1, 1, 1, 0, 254. Because 255 is reserved. We cannot use that. 254 minus 127, there's bias, would be 127. So the maximum number has something of 2 to the power of 127. And the significant, we make everything as 1. So it would be 1.11111111111, 23 bits of 1. How much would it be? 1.11111111111. It is very close to 2, because this is 1 plus 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 3 plus 2 to the minus 4 plus 2 to the minus 23. If you add them together, it is not 2, but it is very close to 2. So the largest value would be, the exponent is 127, the significand is 2, so the largest number is 2 times 2 to the 127, which is about 10 to the 38. Again, you see you have a number of 38 digits in decimal. In binary, it is like that, okay? So this is another example. For double precision, we can do the same thing. When you want to find the smallest value, you cannot put 0 because it is reserved, but you can put 0, 0, 0, 0, 1 for the smallest one, and for the largest exponent, you have to put 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. The last one is 0. You cannot put 1, 1, 1, 1, 1, 1 for the largest one. So the smallest value would be 1. So the exponent would be this minus bias. The bias is 1023, which becomes minus 1022, and the significant would be 1 because it is 0, everything is 0, 1.0, and the number would be 1 times 2 to the minus 1022, which is about 10 to the minus 300. So we have a resolution of 300 decimal fraction parts. The largest value would be this one, which is a 2046, because 2047 is reserved. 2046 minus bias becomes 1023, and the significant, again, everything is 1. It is very close to 2, so the largest number would be 2 times 2 to the 1023, which is around 10 to the 308. So a decimal number with 300 digits. You can go up to that number. Anything beyond that cannot be represented in double precision floating point, overflow. So there is a limited precision. It is not unlimited. You cannot say, okay, I can represent any number to that. Even in terms of the smallest number and the large number, and even to the number of fraction parts that you would like to have. You cannot have everything. It is 32 bits or 64 bits. It's limited. So, for example, as I showed you, it was around 2 to the minus 23 for the single, and 23, 2 to the minus 23 would be what? 10 to the what? 10 to the what? So we have to take logarithm of both sides. The logarithm of this would become this, and here we have logarithm base 10 of 2 to the minus 23, which would be 23 times 0.3, which is 6. So it means that we have 10 to the 6 precision. We have 6 decimal precision, like you have a number of 6 digits precision. For double precision, it is minus 52. So again, if you calculate the logarithm of that, the logarithm of 2 minus 52 to minus 52 would be 16. So it means that you have 16-digit precision. In decimal, in binary, you have 52 digits precision. Example. Minus 75, I guess I have showed you before. Minus 75, yes. So minus 75 is minus, so the sign bit is 1, okay? And then we have, it's hard to calculate that. What I am making is I am making 1.5 times, this is 0.75, yeah? Okay? This is 0.75. So if I want to represent this, then it means that I have 1 with 0.5. What is 0.5? 0.5 in binary is this. This is 0.5. So this is my fraction part, and the exponent would be minus 1. And I have to add the bias to that. So the bias would be, the fraction is this, you see? The fraction is just, where was the fraction? 1.1. The fraction is 1, so this is the fraction part, and the exponent would be minus 1 plus bias. Bias was 127, so the exponent would be 126, which is this number, 0, 1, 1, 1, 1, 1, 2. So let's put them together. For the sign, I have 1. For the exponent, I have this, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, this is exponent. And for the fraction part, I only have a 1 here. So 1 and 22 bits of 0. So this is 32-bit single precision representation of minus 75%. Yeah.
Can you go back to how you go from minus 0.75? How do you go like
1.5? Yeah, you mean?
Yeah.
Okay. From the reverse part, it is easy. Do you accept that this is 0.75? 1.5 divided by 2. Yeah? 1.5 divided by 2. Divided by 2 is 0.75. So from the reverse part, it is easy. So you know this is 1.5 divided by 2. But how did I reach the 1.5 to that? Okay, to do that, as I told you, we have to make this a number of something between 1 to 2 times 2 to the something. Okay? So for me, what I do with these numbers, I start multiplying it by 2. So if I multiply it by 2, I get this one. Yes? So it means that 0.75 is 1.5 times 2 to the minus 1. Because I multiplied it by 2, I get this. So if I multiply this by 2 to the minus 1, I get that one. So for this is, but I hope that I have some, let's say, more complicated, because 0.75 is very easy. Let me see if I have another example. So this is the single representation, this is double representation. So they are simple. The point is here, you see? The point is this, yeah? This is the point. This is 0.5. 0.5, and we have 1 in front of that, so it is 1.5, and then we have the exponent, which is minus 1. So it is 1.5 times 2 to the minus 1. Okay, we have to calculate more. Do we have, did I have more? Oh, no. So it's the reverse. The reverse is simple, yeah.
I got the idea, but the 1.5 is still in decimal.
1.5?
It's still in decimal.
Decimal. Yes, 1.5 is decimal. So how do we represent it in binary?
It's like 0.1, 0.1 in binary, but
1.5 is decimal, okay? But I made it 1 plus 5, okay? 0.5. I don't look at this 1 because the 1 is always at the beginning of the fraction part. So you disregard that. So 0.5, what is this number in binary? 0.5 is 2 to the minus 1. Okay? So it is this number in binary.
how the 1.5 is decimal and multiply the 2.
You mean how 0.5 is 2 to the minus 1? You understand this?
I understand.
Okay. Okay. You understand it. If you understand that, no, okay. Yeah, there are different steps. You have to make them separate. One step is the fraction part, and then the other one is the exponent part. For the fraction part, here we have a fraction part of 0.5. 0.5 in binary is this. You know that. You said that you know that 0.5 is 2 to the minus 1. Yeah? So this is the one. This is the, you know, if you remember, you know, not in your course, in ITI 1100, when you have a number like this, 1010.1001, what is this number in decimal? You start putting the value of each digit. This is 2 to the 0. This is 2 to the 1. This is 2 to the 2. This is 2 to the 3. Okay? But what about the fraction part? This is 2 to the minus 1. This is 2 to the minus 2. This is 2 to the minus 3. This is 2 to the minus 4. So what is the value of this number in decimal? Okay, let's calculate. 1 times 2 to the 3 is 8, plus 0 is 0. 1 times 2 to the 1 is 2. Then 0 times something is 0, plus 1 times 2 to the minus 1 is 0.5. 2 to the minus 1 is 1 over 2 is 0.5. Then we have 0. Then we have 0. Then we have 1 times 2 to the minus 4. 2 to the minus 4 is 1 over 16. 1 over 16. How much would it be? 1 over 16. You help me.
0625.
0625. Yeah?
I think it's only 10.
10. Okay. So 0625. Yeah. So you add 0625 to 05, which is 5625 with 10. So this number is 10.5625 in decimal. Okay, good? Okay. So calculating from the binary representation to decimal would be easier, I guess. Let's see. That conversion, I guess it's more tricky. So here it's simple. This is the exponent. This is the fraction. So the exponent is 100001, which is 1 is, this one is 128. This is 1, so it is 129. Minus bias is 129 minus 127 is 2. So the exponent would be 2. So we have this times. And the fraction part is this. So we have a 1 in the front of that, 1 point this, 1 point this. So what is this? This is 2 to the minus 1, which is 0. This is 2 to the minus 2. 2 to the minus 2 is 0.25. So this number is 1.25. This is the number. 1.25 times 2 to the 2. 2 to the 2 is 4. 4 times 1.25 is 5. So this number is plus 5. Got it? Yeah? This number is plus 5. Actually, plus 5 could be represented by an integer binary number, but now we wanted to represent plus 5 in the single precision floating point, which would be like that. This is plus 5. And did I calculate it correctly? Ah, God. Minus? Oh, it is 1 here. So it is minus 5. Why did I write plus 5? Minus 5. Sorry, minus 5. Okay? As I told you, 0, 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 1, 1 for the exponent is reserved. And they are denormal numbers. 0, 0, 0, 0 is reserved for that. If you have this exponent, then you don't have a leading 1. It is not 1 point this. So only this exponent have a leading 0 of that. So it will make a smaller value of numbers. So, and it is very good for representing 0 also. Because if you put 0 as the exponent, and if you put 0 as the fraction, then you get something like that, which is 0. So exact 0. But depending on the sign, you could have either plus 0 or minus 0, which they're the same. 0 is 0. It doesn't have any sign. So for 0, the representation of 0 in floating point is this. 0, this is the sign. So it would be either 0 or 1, but the exponent is 0. The significand is also 0, so everything is 0, and in this way it will become 0 representation. And also, if it is 1, 1, 1, which I told you it is reserved, and we shouldn't use it for the regular numbers, then it means if it is 1, 1, 1, 1, 1, and the fraction is 0, 0, 0, 0, 0, it represents infinity. When you want to show that there is a large number, that we cannot represent it using the floating point that we have, either single precision with its limitation or double precision, then you use this number. It means infinity. If you put some fraction other than 0, then it means that not a number. For example, when you divide something by 0. If you divide something by 0, then it is not number. Dividing by 0 doesn't have any meaning. So you represented it with none, not a number. And how do you represent it? You represent it with 1, 1, 1, 1, 1, 1, 1 as exponents, and then something other than 0 for the fraction part. So this is none. 0 times 0. Okay. Now that we saw how to represent floating point, how do we add them? And then how do we multiply them? How do we do that? You know how to do that in decimal? For example, let me write something for you. For example, we want to multiply 12 by 25. This is two numbers. So what is the normal representation? 12 would become 1.2 times 10 to the 1. And 0.25 becomes 2.5 times 10 to the minus 1. Okay? Agree? Everybody okay with these two numbers? This is 12. This is 0.25. Yeah? Follow? Look at these numbers. If you have questions, ask me. So these are two numbers. We would like to add them together. 1.2 times 10 to the 1, 2.5 times 10 to the minus 1. How could we add the two numbers which have some kind of multiply by an exponent? How could we do that? Tell me. How do you add them together?
Add.
Who told me? You told me? Who? Yeah, tell me. Suggest, it's okay. Yeah, to you.
So it's 3.7 times 10 to the negative times 10 to the.
You calculated the result. How did you do that?
Well, you add the non-exponent and then you add the exponents together.
Yeah, you just adding them together and then
You add the exponents like you do in math.
You mean 1.2 plus 2.5, which would be 3.7? Yeah? But they have different values.
You can add the exponents, so 10 to the 1 plus 10 to negative 1 is 10 to the 0.
We are not, you are talking about multiplication, I guess. We are adding this thing. Yes?
We have to find them to be the same exponents first and then add them.
Of course. When you have two numbers, a times b to the n plus, let's say, c times d to the m, b. You have to make the same exponent of these together, and then you have b to the something, and then add the mantissa together, okay? So which exponent do we convert to the other one? We have an exponent of 1 here and minus 1 here. What do I do? Yeah? Which one do I convert? You said that I have to make them the same. So I have two exponents. One of them is 1, the other is minus 1. What to do?
Either one would work.
Either work. But
It's different, like where you move the decimal place.
either works, but since we might have some kind of limitation in the precision, we have to get the smaller number and make it as the bigger one. Here we have 1 and minus 1. What I do, I am doing to convert this number to something with an exponent of 1 instead of minus 1. So I want this number 2.5 times 10 to the minus 1. So I want it to become 10 to the 2 to the plus 1, as it was the first number. So it means that I have multiplied this part by 10 to the 2, yes? So now I have to divide this part to 10 to the 2, yes?
So why we not convert the bigger number?
As suggested, what was your name? Anas. Yeah, was Anas suggested, you can do either of them. But since at the end you would have limited precision, then if you made both of them to the smaller one, then you might get something out of the precision, which is not good. So it's better if we make them the same as the bigger one. You can try it. You make the smaller one, and then the result would be okay. But there might be some problems in the digits at the end. So to be safe, I get the bigger one, which is 1 here. So 2.5 times 10 to the minus 1. I want to make it something with 10 to the 1. So it means that I multiplied this part by 10 to the 2, which becomes 10 to the 1. So if I multiply this part by 100, 10 to the 2, then it means that I have to divide this part by 100. So the result would be 1, 2 to the left. So this is the one. So this is the same as 0.025 times 10 to the 1. Here it is 10 to the 1. The point is that we made both of them 10 to the 1. Now we can add them together. So we have 1.2 times 10 to the 1 plus 0.025 times 10 to the 1. Now we can add them together. 1.2 plus 0.25 times 10 to the 1. Okay? So what would be the result? 1.2 plus this would become 1.225 times 10 to the 1. So this would be the result. 1.225 times 10 to the 1. And then after we calculated the sum, we have to normalize it again, if it is not. But here it is normalized, so it's okay. Because this one is something between 1 and 10, so it's okay. But when we add them together, it might get out of the range, from 1 to 10. Then we have to normalize it again. Okay, so let's do another example. So this is how we do it in decimal. The same thing we are going to discuss in binary. This is again a decimal. So 9.999 times 10 to the 1, which is actually 99.99. and this is 1.610 times to the 10 minus 1, which is actually this number, 1.61. Okay, we are adding these two together. To make them together, we have to make the exponents part the same. So we align the decimal points, shift number with a smaller exponent. So this number becomes, this one becomes 10 to the 1. So it means that we multiply it by 10 to the 2. So this part would be divided by 100, which will become 0.16. Now we can add them together. The exponent is the same, so we can add them together. And when we add significant, 9.99 plus this, it becomes 10.015 times 10 to the 1. Now it is not normalized. This is what I told you. After you get the result, you have to see if it is normalized or not. So it is not normalized, so we have to normalize it. To make it normalized, we divide this by 10, which becomes 1.0015. Since we divided this by 10, we have to multiply this by 10, which becomes 10 to the 2. So the normalized number would be 1.0015 times 10 to the 2. This is the normalized number. And then if there is a rounding required, for if it is more than the precision that we are using, since first I told you we have 4 digit, so it is 5 digit. We have to round it. To make it 4 digits, so 1.5 becomes 2. 1 point becomes 2. So this is the final result. And it is normalized and it is rounded because it was more than 4 digits. We have 4-digit precision. The binary is the same. For example, I want to add these two numbers in binary. One of them is negative, the other is positive. Again, I have to make the exponent the same. This is -2, this is -1. So I have to make them similar, to make them the same. So I will multiply this by 2, which becomes 2 to the -1. So I have to divide this by 2. So this would become the binary number. So this is the first one, which remains the same because it is the bigger exponent. But this one, it shifts right. It is divided by 2. But here, the exponent now is -1. Now I can add them together. 1 plus minus 0.111. If you add them together, then the result would be 0.0001 times 2 to the -1. Now we have to normalize it. Since you see it is not normalized. It should be something between 1 and 2. So we are multiplying this by 1, 2, 3. 2 to the 3. If we multiply this to the 2 to the 3, it becomes 1.0. Then we have to divide this by 2 to the 3, which becomes 2 to the -4. So this number is the same as 1 times 2 to the -4. And 1.0 is the number. So our single precision number would become, the fraction part is 0, the exponent part is -4 plus bias 127, the number would be something like that. So this is the number, 1.0 times 2 to the -4. And here we just stop at the normalizing, but you can also represent it in single precision. For making hardware, exactly what we talked here, we have to make it in hardware. In our hardware, we have something to compare the exponents. Find the smallest one. Then shift the smallest one as much as possible to make it the same as the bigger one. And when we shift the exponent, so then we have to shift the significant to the opposite direction. Then we have to add the fraction part together, and the exponent would remain the same. After we have added them together, we have to normalize it, and after normalizing, we have to round it up. So exactly whatever we did in example. But you see, these steps, they cannot be done in one clock cycle. If you want to do everything in one clock cycle, that would become your critical path, and it will decrease the clock frequency for you. So it is better to make it a pipeline version of that, so the clock frequency doesn't degrade because of this operation. So we use pipeline. So this is the hardware. You see, we just compare exponents first to see which one is bigger. The one would be the bigger one. When we find the difference, then we select that one, either this one or either that one is the smaller exponent. So using this multiplexer, we select the one which should be shifted. So the one which should be shifted coming from here. It is either that one or that one. And this multiplexer is selects that. This multiplexer selects which of these two should be shifted right, and which of these exponent is the smallest one. So it shifted right, this one. It comes from here. We add the fraction part together. We get the result. And then we normalize it, increment or decrement, normalize it, and then rounding. So the same thing that we have talked in the previous slide. Now we have talked about addition. Let's talk about multiplication. Okay, so I guess we can finish this and finish the course. Multiplication is somehow easier. The things that you were mentioning before, it is for multiplication. When you multiply this by this, 10 to the 10 times 10 to the minus 1 becomes 10 to the 10 plus minus 5 is 5. And then we have to multiply this by this. And this comes here, then we have to normalize it, then we have to round it. So somehow we can say that it is a little simpler, but again, it has so many steps to do, and it cannot be done in one clock cycle. So exponents will be added, and then significance will be multiplied, and then we have to normalize results, and then we have to round it. So it's almost straightforward compared to addition. For addition, you have to make the exponent the same and then add the significand. But here, you just multiply them. And the sign should be determined at the end. If both of them are negative, the sign is positive. If both of them are positive, the sign is positive. If one of them is negative, one is positive, then the result would be negative. The same example, you go through it yourself. So the exponents will be added. Then these are multiplicated. And this would be the result. So the result would be this. We have to normalize it. There is no change here. It was already normalized. So we have to round it. So again, it is enough. We had 4-digit binary, and here we have 4-digit. So there is no rounding required. And the sign is positive times negative is negative. So it should be a negative number. And this would be the final result. And the hardware would be, I guess, similar, but a little bit simpler. I say it's similar. And the function, the hardware for floating point, for example, in MIPS, it does addition, which is a little bit hard. subtraction, the same as addition. Multiplication and division is simpler because you just get the exponents, sum them, add them together or subtract them, and then you multiply or divide the significand. That hardware usually calculates reciprocal, so 1 over something. And that hardware could also calculate a square root, which I don't go through that. It is a complex hardware. And also, we need some kind of hardware for converting between integer to floating point or floating point to integer. And these are the hardware that we are seeing in the processor. In MIPS, we have a coprocessor added to MIPS. It has its own instruction set. It has its own registers. If you look at the instructions, then you see this side of your reference is the floating point instructions. We have branch, we have add, sub, divide, multiply, load, and store also. So I will show you some of them to you. The registers will be 32 single precision registers. They could be paired together, become double precision registers. So you can have, so in single precision, you have 32 registers. In double, you have 16. But newer version of MIPS, they have 32 64-bit registers, not 16 32 bits. Okay, the instructions would be load, single load word from coprocessor. So it means that we load from the memory and put it into the registers of coprocessor, which they are F0 to F31. We have load double, so we get 64 bits from memory. We store it in the register, a pair of registers. So the load double always have the destination of even numbers, F0, F2, F3, F4. You cannot say load double to F1 because F1 is not paired with something to make it double. F0 is paired with F1. F2 is paired with F3. F4 is paired with F5. So you have to load double to the F0, F2, F4, F6, and so on. For example, load double coprocessor from coprocessor F8 with this memory location. Again, the memory location is, this is the base address, this is the offset address. So from this address, we load 64 bits, double precision floating point, and we put it to F8. F8 and F9 together, which is 64 bits. We have add for single precision, and we have also add, sub, multiply, and divide for double precision. So the single precision is add.s, sub.s, mul.s, div.s. For example, add.s, F0, F1, F6. So it means that F6. It means that F6 will be added in single precision format to F1, and the result is stored in F0. Okay? Single precision. But if it is double precision, then we have D. For example, you see here, multiply double F4 times F6, and the result will be stored in F4. 64 double precision. You can compare with C, compare the operation LT GT less than, greater than, LE less than or equal, GE greater than or equal with 2 registers. For example, and this will set or clear FP condition bit. For example, compare less than in single precision F3 with F4. So if F3 is less than F4, the condition code becomes 1. And then based on this condition code, we have branch on FP condition code. We can write branch on condition code true or false. So if it is less than that, it becomes true, then this branch jumps to that location. It is taken. If not, it goes to the next instruction, the same that we had before. So these are the examples for you see it yourself, how to rewrite a simple C program in MIPS instruction set. We load them, divide them, and then subtract them. We are calculating Fahrenheit minus 32, and then multiply this by 5/9. So we calculate 5/9 here, we subtract Fahrenheit minus 32 here, and then we multiply this by that. Okay, I am done with the course. So we showed you that the bits 0 and 1s could represent numbers, either integers, either signed or unsigned, or either floating points, either single precision or double precision. And these are the representation of numbers. They have a finite range, limited range. It is not unlimited. You cannot represent any number with the number, a limited number of bits. And instruction set should support arithmetic, but in MIPS, there are limited instructions that we could see. For example, in MIPS, we don't have a square root, but in some processors, we have a square root to calculate a square root. And we have a range and precision for floating point numbers. MIPS IS instruction set only contains the core instructions that it is used more frequently. And if it is not used frequently, then it is not supported. The MIPS instruction set covers all of the operations of the benchmarks in spec-int, the benchmark for integer programs, and it covers 97% of the operations in floating point benchmarks. So that's it. I hope that we could cover the basic points of computer architecture. I remind you from the first session that we had, and I ask you to look at the videos from Dr. Hennessy or either Dr. Peterson to see how computer architecture now is it's moving now, and what would be the future of computer architecture. And the modern computers now, they are based on MIPS. They are RISC architecture, reduced instruction set, which MIPS is maybe the best representation of a RISC computer. And I've tried to show you first the instruction set, tried to show you that not every instruction should be supported. We just use the one which they are more common, and then we built the data paths and the control for that processor. I hope it was good for you, something useful for you, and you learned a little about computer architecture. So if it's okay, we conclude the course here. Thank you very much. I hope you enjoyed it. And if it's okay with you, we can have a group picture together before the. Oh, before that, you make the attendance, please. The password for attendance is last, means the last attendance that you are doing. It is not the last quiz, but it is the last attendance. We will have another quiz asynchronously. You do the last one later in your home. For the next session, we could be in contact with the discussion forum. I will put for you example questions for the final. You worked on them. I told you before, if you don't work on them and I just write here the solution, it doesn't have any good for you. You have to think about them, find for yourself where is your problems, where is your challenges, and then I will help you, I will solve it for you. So please work on them and then announce in the group that we need to have another session. Yes. Next Friday?
Oh, yes.
You mean coming Friday or next Friday? From now, before your exam, whenever you want, we can have a session, a question session, and maybe we can make it online. So everybody come here, but we will discuss and we will solve the problems for you. Okay?
Should we go to pasta Friday?
No. If you say that you need to have, then we will make it online.